Good afternoon, everyone. My name is Tobiasz Górecki. I work in the Satellite Remote Sensing Department at the Institute for Meteorology and Water Management National Research Institute in Poland. Today, I would like to talk about real-time satellite data processing at my institute using CSPP software. In this presentation, I will briefly introduce our operational workflow, the satellite data products we process, and how the community satellite processing package support meteorological monitoring and forecasting activity. I will also present selected application of the satellite remote sensing in weather analysis and environmental monitoring. Because at the end of the day, we use satellite data to understand environment, understand weather, and help people. Okay, there's a small mistake in my first slide. Should be 2026. Apologize for that. Okay, in our institute we use data from geostationary satellite and from polar orbital satellite. Geostationary satellite provide continuous reception of satellite observation with updates every 5 to 50 minutes for our real time. And our institute receive data from MSG and MTG data. So the geostationary satellite have very good time resolution. For polar orbital satellite, we have a very good spatial resolution, but not as good as for geostationary satellite time resolution. And we received a satellite from NOAA 20 and 21, Suomi and PP and Aqua, and also METOP B and C, also Sentinel-1, AWS, so a microwave satellite. Our infrastructure is 3.8 meter dish for high gain signal reception, and we try to high availability computing, ensuring 24/7 continuous and processing. Where is the Poland? Poland is next to the German, and our station is in Krakow, is the southern part of the Poland. And you can see on this image from the right side. And below this map of Poland, we can see two images. One on the right side is the antenna for geostationary satellite. On the left is for polar satellite. Okay, so this is a scheme of processing in our institute. So currently we have only one antenna for polar satellites, but another one will be installed later this year. And first satellites are received by the antenna and then transferred to the processing server and finally distributed to the user. Who is the user? User is a forecaster mainly, and they use this data to monitoring local weather condition, including storm development, precipitation, rapidly evolving cloud system. Next is hydrology department and try to monitoring rainfall, soil moisture, and flood extent, and early warning system. and also climatology and coastal protection. So on the slide we can see how this, in the very general form, how to how satellite data is processing in our institute, in our department. So we try to run fully automatic process chain using, for example, CSPP, Pytrol, and WCSAF, TUMET, and proprietary software. And we generate a wide range of products, including RGB imagery and composition from Meteosat, MODIS, and VIRS. We also use SAF product and Sentinel-1, SAR data, and Sentinel-5P to observation atmosphere. The products are used in daily weather situation analysis and hazard briefing. Every day we have a briefing and we present how forecaster can use and can use satellite data. And visual product support and operation service, cloud cover, precipitation, flooding, and wildfire here. So here is a few examples how this product looks like. We have a fire, we have a precipitation, we have a night VIRS image, soil moisture, and one image from Sentinel-1 data. So how many satellite we reception we can see on this graph. On the left, satellite passes 1 day schedule. We observe NOAA 20, NOAA 21, around 12. And next we have METOP C and METOP B around 8 to 9 a.m. And next we have NOAA 20 and NOAA 21 around 10 a.m. And afternoon we have a METOP B again and a METOP C and twice. And between these two satellite passes, we observe we receive data from Sentinel-1. So this is how it looks like satellite transmission on the image. We have Eastern satellite transmission, Central satellite transmission, and Western satellite transmission. And there are no equal. So the processing time is different from different transmission type. And we have also this beautiful nighttime satellite transmission. And we have detect, for example, cloud from an aura and okay. So during routine operation, we currently follow software. We have a CSPP sensor data record, HIP, MIRS, VIRS active fire, and Polar to grid sometimes. All processing is performed on a single server with 12 CPU and 128 GB of memory. We plan to add more in the future, which will require, of course, more processing power. Therefore, we plan to use our new cluster to processing this data. But before that, we decided to perform benchmark to determine the optimal number of cores required for each program. here is the one node of this cluster. We have 112 CPU and more than 500 gigabyte for one node for processor Xenon. So it's a very good processor. And this benchmark schemes is we run each program 10 times. We analyze execution time, memory usage, and CPU utilization for different number of CPU cores, ranging from 1 to 12. And we benchmark VIRS instrument, ATMS, CRIS, OMPS, SDR version 4.141. This is very important. CSPP HIP and MIRS, and also atmosphere. We don't use this atmosphere product now, but we plan to in the future. And this is the result. What we can see is that from ATMS instrument, only one processor is required to compute ATMS is the least demanding instrument in terms of CPU and memory usage. We can see on this picture. VIRS is the most computational demanding instrument, while the OMPS and hyperspectra instruments require noticeable fewer resources. And we can see on this first upper left image graph for one processor time, total time is around 12 minutes for VIRS, and it's 1 minute for ATMS. And practical all instrument reached performance plateau around 8 CPU cores. Memory usage is for VIRS is about 6 gigabyte, and for ATMS is less than 1 gigabyte. So it's not very very big. Interesting is CPU utilization, because none of the instruments are able to achieve 100 CPU utilization. For example, for VIRS instrument, if we choose 8 processor, the utilization is around 500%. Okay, for HIP programs, compares we perform we use two data from 2 satellites. One is NOAA 20 and second is METOP-C, and we can see that METOP-C has plateau around around 2 processor, and then the execution time is not change. The difference between METOP-C and NOAA 20, it's not very big for memory usage, and CPU utilization is very different from this 2 instrument or this 2 satellite. For example, for the number of processor 8, we have we have a plateau for METOP-C and for NOAA 20, if number of processor is around 10, we have a 600 CPU utilization percent. So for METOP-C, we have no speed up factory for a higher number of processor. For MIRS, we show slight instability with noticeable fluctuation execution time. Have to jump between around four processor and 8 processor, and memory usage is constant. So total speed up is around 4 for 12 processor, and utilization is still around 400. And the first benchmark was made for atmosphere software, and for one processor, total time it's higher than 50 minutes, so it's very high for operation point of view, but very quickly changed to 5 minutes for 8 processor, and it's plateau when the number of processor is increasing. So finally, total time is around 5 minutes. And from user point of view, it would be better to include an option for selecting products for during computation, because number of product from this software is huge, and not necessarily all product will be used from user. Okay, but this is all about a benchmark. Now we can go to the product, and in real time, we processing and visualization of VIRS RGB product and cloud microphysics property, which provide information about cloud microphysics characteristics such as particle size, liquid water content, and cloud phase. And this is how it looks like in the last 5 satellite image from VIRS from our web page. And this is very important for forecaster during day. And why we use polar satellite? Because polar satellite have a very good spatial resolution. It's for VIRS, it's comparing to the MTG, of course. We have a 750 meters resolution for VIRS, and from example MTG FC, we have a 2 kilometers, 2 to 3 kilometers, and higher spatial resolution allows for more detailed observation of cloud feature and physical processes. And this is example. We have a cloud, probably very intense convection system, and on FCE, we don't see detail, and for VIRS we can see. If we zoom in on this, lower cloud top temperature indicates strong upward vertical motion, leading to intense deep convection, rapid vertical cloud development, and increasing severe weather potential, including large hail, demanding winds, and heavy precipitation. In this picture, we can see this red spot in the middle of this cloud system. So in this point, top high temperature is very low, so it's very strong convection. Okay, and RGB product. We can compare MTG and polar satellite data, and polar satellite enable to better distinguish between cloud cover and cloud-free covers due to the higher spatial resolution. Okay, but next step is to use HIP and MIRS data, and we can compute vertical temperature profile and moisture from this product. And this is how it looked like our service providing this vertical profile of temperature and dew point to support forecasting using these two algorithms for hyperspectra and microwave instrument. This red point is the HIP profile, and in the middle, this red is a blue one, and this is a MIRS vertical profile from microwave instrument. They are a little different between vertical profile from hyperspectra and microwave instrument, and from only microwave instrument. And based on the feedback from the forecasting department, we plan to implement temperature and dew point map at various pressure level. This is very important information from forecaster, at least from 4 pressure level. And this is how this looks like. And another thing is that currently this product uses GFS, a global numerical weather prediction model, as the initial condition from computation. A better solution would be to enable to user or to use of local version of models such as Icon, Cosmo, and Alaro. Okay, I noticed that one software MIRS sometimes has problem, or how to say it, have problem at upper atmosphere from estimate temperature at upper atmospherical level, for example 300, probably due to detectable surface influence, and this MIRS program underestimated temperature value. And we can see this over the ocean only. And this is the problem, because if we have, we can see on this right, on this left, my left image, we can see that over water surface, over sea, we see a lower temperature at 300 hectopascal level. On the other hand, initial observations suggest that HIP may overestimate temperature at 300 level over ocean surface. There is no cloud over in this region, in the Sea Baltic. So it's not because of cloud. This is because algorithm or because we don't know exactly. And RGB air mass products show red color in this area, which usually indicate dry and warm air in the upper atmosphere or stratosphere, often associated with dry air intrusion and atmospheric dynamics. So this HIP software, it's quite good. We can expect it higher temperature over sea, Baltic Sea. Okay, we can also may use this HIP software to monitoring atmospheric chemical composition, and this is an example of event which occur in 2025 over Poland. This is probably because of the smoke and ash from Canada, where the smoke and ash were transported across the Atlantic, and we can observe this in our institute. Hyperspectra atmospheric product enable monitoring of the this smoke and ash, and we can even observe a vertical profile of this carbon monoxide. Okay, we can also use microwave instrument ATMS to monitoring weather. This is because on average cloud cover in Poland is about 70%. And this is example of the sun day in Poland. And microwave instrument provide observation of physical process occurring within cloud. And this is how it looks like a TMS channel from a few channel, and this channel primarily represent atmospheric and water vapor and hydrometers at different atmospheric level, and we use polar to grid to perform limit correction on the TMS brightness temperature channel, removing scanning angle dependence bias. And it would be good if we use this limb correction also from METOP BNC microwave instrument, and in the future from METOP second generation. Okay, and this is example how we can use this this data from from microwave instrument, and this is a cyclone which which occur in Poland in 2025. And we can see how hydrometeors looks like from the different high. So we have a 7 kilometers, 6 kilometers, 5 kilometers, and 3.5 kilometers. And we are also able to track the movement of the hydrometeors, and so we can track precipitation or changing dynamic in the cloud. And we also use fire temperature, and this is example how it looks like in our web page. We monitoring fire across Europe because many of these countries are popular summer tourist destination for Polish travels. And this is example how we can use active fire product to monitoring white fire. This is a white fire from 6 May 2026. On the fire temperature RGB product, we see this red spot, and we also see this fire on the active fire product. And we can use active fire product and merge it with, for example, Modis land cover product in order to better understand land types associated with fire occurs and to estimate the probability of the future fire events. And we also try use flood detection via software, but because of the spatial resolution, we only can use this product for very large scale floods. And this is example of the floods from 2024. And cloud-based high, this is very important product. We plan to compute, and we plan to also validate this product using celliometers from our station. Okay, that's all. Thank you very much.
Thank you, Tobiasz. I think we have time for maybe a quick question, if there's a question in the audience. I don't see anything online.
Thank you very much for the presentation. Just on my side, wanted to know, you mentioned that you're planning a second antenna, second chain.
Yes.
When do you expect to have that implemented and operational?
Probably next year, because this is a long. Probably next year. I think next year.
Would that be the middle of next year, the end of next year, or? Sorry.
Could me? What is?
Would it be the beginning of next year, the middle of next year?
Begin. I think.
Okay. Thank you very much.
Okay, thank you very much, Tobiasz. Our next speaker is Timo Ryyppö from FMI, who will be speaking on FMI Arctic Space Center, current and future satellite missions, and CSPP-based services.
Okay, thank you very much. So my name is Timo Ryyppö, and yes, the pronouncing of my last name, it's not so easy. So we were discussing about that on the during the lunch. So it's, yeah. Yeah, I can teach you later. Yes. Yeah, but you can call me just Timo, or as at my workplace, Omit. So we have actually 4 Timos, so we need to have like nicknames for everybody. Okay, but yeah, I'm here to talk about the Finnish Meteorological Institute and our Arctic Space Center and its current and future satellite missions, and of course the relation of the CSPP-based services. And we have a headquarters in Helsinki where we have the geo reception and using the EUMETSAT, but that is now unfortunately totally excluded from this presentation, and I'm just focusing on the polar orbiting activities we have in our Sodankylä sites. So the content of the presentation is, I would say, a general introduction of our FMI Arctic ground station, the infrastructure and the services we have, and then, of course, the CSP-based products and the services, and a little bit of the history of that and the current situation. And then I will talk a little bit about our future plans and a short, let's say, discussion and a request for the community. And it won't, let's say, follow the content like this, like 3 parts, but especially the plans I will be introducing after I told about one of our services and then what are the plans for that service. So I think it's easier to have the whole timeline for each of the services at time. Okay, and we are located pretty high north, so 67 latitude. So, well, I don't need to explain the details for this community why it's good to be at so high north latitudes. But we can see about 10 out of 14 overpasses per day for one satellite that is in a polar orbit. Our friends in Norway, especially in Svalbard, they do better, so they can see all the passes. But then I have a few other stations as an example, one in Italy and one close to equator, and the numbers of how many passes they can receive per day. And even Finland is actually a pretty long country, so over 1,000 kilometers wide, so that's why it's good to be up in Sodankylä, not in our capital Helsinki, where usually we try to concentrate all our activities, but I would say this is one activity that we want to get out of the capital to like a remote region. And just in the video, it's just showing the visibility cones of different stations, and as you can see, the polar orbiting satellites they are very visible in the northern parts. Okay, and then what we have in our station. So at the moment we have 4 working antennas and 1 antenna that is not anymore working. So after almost 20 years, we need to decommission it. And we have named our antennas called a SOD antenna number, and we have reserved 2 numbers for the antennas. So there are high hopes that we could get even 99 antennas. So we have already reserved the space for that. But yeah, we started the activities with 2.7 meter ACMAD antenna from sea space, and it was mainly used for the EOS missions and later expanded for the NPP. Then we have 2 larger scale antennas, 7.3 meter antennas that both work in X-band, but the latest one, the SOD 03, has also S-band, so we can actually communicate with the satellites. Yes, and those 2 big antennas, they have like a shared schedule, and we can like cross-use the antennas for different missions. And they've been taking operations 2011 and 2017. And the newest add-ons, they are a little bit smaller one, antennas, 3.7 meter X and L-band antennas called SOD 04 and SOD 05. And basically, we also wanted the L-band capability that we could, for example, support the EUMETSAT, and there are some, for example, Arctic weather scientists working in L-band. So even most of the, let's say, ground stations are going for the higher frequencies, Ka and other, even a little bit lower ones, but it was because of our needs. And it's not just the antennas. We have a on-site data center that has like an, I would say, a full capable data center. So it has a redundant heating, ventilation, everything, UPS, and we also have a backup generator. So every year there will be a power cut, so we can still be up and running and produce our own electricity. And then we have on-premises hosted cloud services and data storages. So basically, we are not just relying some, I would say, real clouds, but we have like an on-premise cloud services available in-house. So for example, we can use the simple storage service S3, and then we have our virtual servers, and we can actually provide a remote access for our partners and customers, so they can process and work next to the data. So it's actually pretty nice and easy that if you don't have, for example, resources at yourself or your startup company, you can come to talk with us, and we can arrange you the servers, and then you can work next to the data, and maybe someday, for example, grow to a big company like the Finnish company ICE is nowadays. It started as a small one, and now it's huge and one of the biggest synthetic aperture radar companies in the world. Okay, this is just an overview and nice picture of our station. So we can see two of our big large-scale antennas, and you can see there is a riser on both of the antennas. So to get a clear visibility, we need to raise the antennas about 10 meters high to see above the tree line. And we didn't want to cut all the trees, because the trees are also our laboratory, and we want to investigate the trees. So it was like a mixture that how many trees we can cut or how high we need to raise our antennas. And in the background, there is a 33-meter dish antenna that is, let's say, not us and not anymore exists. So it was an ACMAD radar receiver that was decommissioned after 40 years about a year ago. Okay, and then what are we doing and what are our satellite missions? So we have some on-demand activities. That means that we have some customers that are requesting us to receive data from certain satellites. So this is that we will schedule certain passes to our antennas only when requested. So not all the visible, but let's say from maybe 2 to 5 or 7 times per day per satellite. At the moment, we are receiving Haiyan 2B and 2C for the EUMETSAT, or it's like maybe a little bit more complicated way. So it's basically we receive the data and send it to ENSOS to China, and then back to EUMETSAT, and then EUMETSAT is distributing it to the member states. Then we are also receiving the Cosmos SkyMed and the Cosmos SkyMed second generation radar satellites, and that's for the CS monitoring for the Copernicus Marine Environment Monitoring Service. And then we are actually using S-band downlink to receive data from the PATS, Spanish PATS and South Korean COMSAT 5 satellites, and that data will eventually end up to NOAA and the NOAA weather models. But then we have the direct broadcast activities. That is basically, I would say, the main activities. And for X-band, we are at the moment receiving the NPP, NOAA 20 and NOAA 21. And then L-band, METOP B and C, and then also the Arctic weather satellite, that is the prototype for the EPS Sterna constellation. So I'm not talking about the Arctic weather satellite more in this presentation, because just after me, Alessio will provide a full presentation of the Arctic weather satellites. And then, of course, we are planning to start receiving the METOP second generation, the first 8 that is already flying, and then when available, the 1B as well. And the usage for the direct broadcast missions is the CS monitoring, atmospheric compositions and gases, activiers, weather service. So basically, the same topics as I would say everybody are doing in this room. Okay, and a little bit of about concept of our operations. As we have 4 antennas, 2 bigger ones and 2 smaller ones. So we have put the antennas to work as a pairs. So basically, it doesn't matter which antenna we use for which satellite missions. So using intermediate frequency matrices, we can route the data to any output we want. So basically, we can get an it's like a matrix style approach, and we can, let's say, do more than with just like a straight pipeline where it's just one satellite, one antenna, and one output. This gives us the redundancy and the flexibility, and also we can bypass some defective components. So, for example, a few years ago, we had a very big problems with one of our antennas, and it was down for a few months. So basically, we lost 25% of our capacity, but with like an advanced planning, we were able to serve the customers 95%. So it is, let's say, pretty good numbers, but it wouldn't have been possible without this kind of matrix-style approach for our operations. Okay, and this is basically what it looks like. So we have about 80 passes per day. That is about 30,000 per year. So on the right-hand side, there is the cumulative sums for a 24-hour period for each of our antennas. And in the lower level, these are the direct broadcast antennas, and they both have like 3 satellites in the schedule, and it's like a pretty easy to predict what will happen in each of the antennas. And the lower, the upper part is for basically those on-demand missions, and they are very unevenly distributed. And then we need to try to mix up and try to work out that how we can manage our schedules. And if you combine all of these antennas, it's the left-hand side, the big picture, how it looks, and how basically the receptions are distributed per time or basically hour of the day. And we have like I would say intelligent planning system. So I said we have like a shared schedules for the antennas, and then we have make an in-house system that use the satellite priority list, and then can distribute different satellites to different antennas to be able to, let's say, fulfill all our needs and the customer requests. So it's I would say it's a very nice tool, and it's a fully automated. So basically, we need to only touch the system only if there are some issues and errors. That usually happens during the weekends and nighttime. So unfortunately, not during the office hours. Okay, and then some CSPP-based products and service we are doing. So first, a short history. So we started to use the International Modis and Air Processing Package IMAP in 2008, and we use it until 11th of May 24. So basically, that was the day when the Terra direct broadcast finally died or was shut down and wasn't recovered anymore. But since 2012, we have been using the CSPP, and we started as a beta tester. So thanks to the CSPP people that we were able to get the software a little bit earlier than, let's say, other people, and we were able to test that. And nowadays it's used for almost all our direct broadcast missions. And it's a very user-friendly software, and it's like a turnkey installation. So basically, if you have once installed the software and then you're doing it the second time, it doesn't take much. So maybe within less than an hour, you can start processing when you have just a place where you start using it. So it's a very, very nice software. And okay, and nowadays it's the Suomi NPP and JPSS missions that are, let's say, our main missions, and where we use the CSPP products. And we can see about 30 passes per day for all of these 3 satellites, meaning that we are processing lots of data. And the background image is actually the first image processed by CSPP ever. So at least outside the Wisconsin University. So I think it was because of the time difference, because the morning was in Europe earlier than in the US. So we were able to process the first image, and thanks to Liam, I got the software, and we were able to, let's say, beat the Swedish colleagues also on that. So there's always like a friendly competition between Finland and Sweden, and we were maybe 1 hour in advance doing the first image with the CSPP. Okay, and one of our, let's say, big topic where we use the CSPP and direct broadcast is the satellite-based wildfire service. In Finland, we are doing a national service for our Ministry of Interior. So basically, we are receiving the satellite data from the Suomi NPP, NOA-20 and NOA-21, and receiving the data in Sodankylä site, processing it, and identifying the hotspots and active fires, and it's based on the CSPP SDRs and the active fire. Of course, there are lots of, let's say, fires or what looks like a fire. So we are filtering out any known location that provides the false alert. So metal smelters, greenhouses, sun glints over the sea, to be able to, let's say, better serve our rescue service. And once we have filtered out all these false locations, then we at least think they are real alerts, and the rescue service gets automatic notifications of these. So again, this is like a fully automated chain. And Finland is pretty well covered by, let's say, people, even it's still a little bit sparsely populated, but still like several first alerts from the satellite comes from this service. Of course, it's not always the real alert, because there was one case that during an autumn they were creating a new road, and during a cold time they made a nice smooth asphalt which was very hot, and the rescue service went there to inspect that. Okay, you have made a very nice surveys and a new road, but it's not a fire. So because it's looked like a too hot spot for the satellites. Okay, and this is one of the events. So we have some forest fire, and even for us, this was a big forest fire. It wasn't so big, but in Finland scale, it was big. But basically, it's there's an maybe 5 years ago there was a fire that we were able to monitor from the satellite. So the fire started as a pretty small one, and then grew up during the few days time. And it was maybe about 20 minutes after the fire started, the first fire or the first alert for the fire service was issued. It was like a very remote place, so it took some time until the people and the satellites noticed the area. And this is the same area, so there's a background image of the burned area, so it's a Sentinel-2 image, and the dark color is basically the burned area. And starting from the left side image, you can see that the fire started on the right side, so basically from the east side, and then after 24 hours, it was spread to the whole of the area, and then later it was ending to the west side of the area, and we were able to monitor the fire and also provide some information for the rescue service on how the fire evolved. We are also doing a service, Europe-wide service, so not just a domestic one. So we are providing active fires for the Copernicus Emergency Management Service. So it's a service that provides the information of the active fires and also some extent of the fire areas or burn areas, and also impact assessment of the fire damages. And because we cannot cover the whole of the area of interest in Europe, so there's like distributed ground stations around Europe, and we are responsible of the northern part of the Europe, and then we have a partner who is responsible of the southern part of the Europe, and we are using all the Terra, Aqua, NPP, and NOAA 20 satellites, so not yet NOAA 21, so it's not a mistake that it's missing, but the FIS system is not ready yet to start using the latest NOAA satellite. But again, we are using the CSPP active fire to provide, of course, the active fires, but then we also use the Atmos to get the clouds, and the clouds we need to create the daily mosaic. So we need to also we combine from the overpasses and do the daily mosaics with our in-house Python tool. So basically, if there's an overlapping, when there is an overlapping passes, we select the pixels that are, let's say, the best pixels, meaning that no clouds or the sun elevation is the highest one. Okay, and this is an example of this FIS web portal where you can see the fire. So this is the current fire season. So basically starting from this year, and all the fires, the blue ones are older ones, and the green ones are the latest fires. But as you can see, there's, let's say, unfortunately lots of fire. But especially in Ukraine and Ukraine east border, there are lots of fires, and even this is a forest fire service. Unfortunately, not all the fires are forest fires, but something else. But you can also map those kind of fires. So of course, the satellite doesn't know if it's a forest fire or what. It's just a fire or some very, very hot spot. Okay, and then totally opposite thing. So going to the winter and the Baltic Sea ice monitoring. So Finland is basically an island because 90% of our import and export goes via sea routes, and the sea that is around Finland freezes every year, more or less. We have a lot of icebreakers that try to keep our harbors open, and then we are providing satellite images for the icebreakers that they know where to go and assist. Mainly this service relies on the radar images, synthetic aperture radars, because of course it's the winter time, and usually during the winter time we don't have so much light and there are so much clouds, so we are forced to use the radar images. But it's not just the radar ones. So especially during the springtime, we can use the optical images to monitor the Baltic Sea ice. And yes, the radar images, they are many times very expensive, and they are not available so evenly around the day. So they are mainly flying on the dawn dusk orbit. So it means that they are not, I would say, available in the morning and then in the late evening. And during the springtime, there can be a very rapid changes in the ice conditions. So it's very good that we can also have some optical images to provide to our ice service. And also the optical instruments, they have so much more channels and wavelengths compared to the radars. And then, of course, VIRS day-night band and thermal emissions band for the nighttime observation. So it's a very good add-on. And the optical processing is done with the CSPP and the visualization with the PyTroll. And yes, the PyTroll, it's just, or actually the CSPP polar to grid functionalities are provided by the PyTroll library. So there are lots of, let's say, well, same people are developing the same system, polar to grid and the PyTroll. So it's yes. Okay, and then we are doing also some satellite-based flood monitoring, and currently it's we are again using the synthetic aperture radars, but and how we are doing it, basically we are receiving radar image, we detect all the water bodies, remove all the natural water, and what is left is something that shouldn't be there. So basically that's the flood. And then we put that on the map, and we can provide the flood estimates for the authorities. But CSPP has the flood detection algorithms that I'm hoping that could help us. So currently in Finland, for some reason, we want to use the planes to detect the flood, and it's very pricey. So these numbers are from a real case that actually the flying over the flooded area was almost 20,000 euros, and the latency was several days. So it's not very useful to at least the live monitoring. With the radars, we could get, let's say, lower price and less latency. Of course, the resolution is not so good. But I'm hoping that the CSPP flood detection could help us for the satellite-based flood monitoring, because there is so much high revisiting rate for the VIRS data, so we can get lots of data from the Finland, and even the resolution is not so accurate or high with the optical images. We could maybe monitor the places more constantly and then focus on certain places where, for example, to take the more accurate radar image. Of course, there is a little bit that is worrying me, because Finland has a lot of small rivers and lakes, and if the resolution of the VIRS, for example, is good enough, but I need to test that and see how it works. Okay, then we have the SANSA service, so which is providing the different kind of atmospheric compositions, and we are actually doing this with the Jeanjean. So we are getting the observations from two sides of the pole, and it's like a real-time, almost real-time product and service we are doing. And the SANSA service, it's relies also for the CSPP, and we started it with the OMI instrument and called it the very fast delivery, but then changed it for the SANSA service. And we have heard today that, or discussed already, that the NASA Direct Readout Laboratory has ended the IPOP development, the software is frozen and archived, and now they're shutting down the ancillary data. So there might be a gap how to do things, but now I'm hoping that, or heard that there should be, and hopefully will be, also the OMS level 2 products under the CSPP that would, I would say, solve the issues, and there will be on Thursday a presentation on that. 1 minute. Yes, and then for a last slide and for the topic, so there was a few topics that you could, let's say, submit the presentation, and there was the user needs for the future satellite missions and some general issues affecting the direct broadcast community. So what I'm bringing up for the discussion, and maybe during the coffee time, is the Sentinel-3 and the lack of its direct broadcast capability. So we have a very good satellite flying already 3A and 3B in orbit, and 3C and 3D to be launched, and they have like instruments that are MODIS-like and VIRS-like, but their near real-time data is about 3 hours or less. That is not a real-time data for me. So maybe if people are talking with right persons in right places, people could push maybe Isa, you might know. No, Nick. Yes, we can talk at a coffee break, but yeah, but this is, let's say, a wish slide that I would hope we could have a direct broadcast in the Sentinel-3. Okay, and that's it, almost respected time, hopefully.
Thank you, Timo. Do we have a quick question for Timo? Leon?
Very nice presentation. So for the OMS data, NOAA received the request from FMI to upgrade the NOAA 20 to higher spatial resolution. I believe that's already made available. Recently, we would love to hear your feedback on using that data. Thank you.
Yeah. So you mean that the OMS?
Yeah, the OMS ozone data.
Yeah. Yes. Yeah. We had I think it was that you can do some of the OMS data, but not all that we are wanting to do. So basically, you're still relying on some part of the IPOP product or IPOP software for that. So it was, yeah, I thought it would be, let's say, easier to do it, but there was some issues that's why we couldn't do it. I don't remember now all the details, but I can find out and talk with you.
Thank you. We'll follow up with you on that. Thanks.
Yeah.
Okay, thank you, Timo.
Thank you.
So we'll move on to our next presenter and final presenter of the session, who is Alessio Canestri from EUMETSAT. And the title is EPS Sterna and the Arctic Weather Satellite.
Good afternoon, everyone. It's nice to be here, guest in this community. So I will give you an introduction to EPS Sterna. I apologize in advance for not showing you any data, but this is because the mission is not yet ready to fly, but hopefully will be ready soon. So let's start with the name Sterna. So Sterna is a Latin name for the Arctic stern, which is a bird which is migrating from the Arctic and the Antarctic throughout the year. This is a kind of symbolic of low Earth orbit satellites. That's why this name was chosen. Main objective of the mission is essentially complement observation from our backbone missions, in particular EPSSG, NOAA, and also the Chinese meteorological satellites. By doing so, we will provide a wealth of data which would improve global numerical weather prediction models and as well as nowcasting application, especially at high latitude. We'll come back to this in the next slide, showing you how the constellation will is expected to significantly improve the number of observations and also the revisit time on the northern hemisphere. And of course, as we will provide more data more often, we also expect to contribute to climate monitoring and global reanalysis of data. So few programmatic features of this program. So first of all, this is a fully funded EUMETSAT program. So that means EUMETSAT is responsible for the entire system, which means the ground segment, procurement of launch services, the LEOP, the system operations, and as well as the management of the constellation. We cooperate with ESA, which will be the procurement agency for the space segment. And we have a cooperation agreement with ESA on that. Also, another important feature is that the Sterna satellites are recurrent models of the ESA Arctic Weather Satellite mission. This was an important programmatic assumption, which allows us also to deliver the mission in a relatively short time. So we expect only very minor modifications for the constellation on the space segment, which is typically one of the drivers for the delivery of the system in orbit. We are also assessing cooperation with other partner agencies, in particular with NOAA, and not only for exchange of data, but also for acquisition of data in the Southern Hemisphere, which would significantly improve also the timeliness for global data. Yes, the mission will have a duration of 13 years, and we expect to deploy the constellation in 2029. So this is just giving an overview of the constellation. First of all, so we will have 3 orbital planes, and you can see on the bottom right in red how these orbital planes are nicely complementing the other legacy missions such as JPSS, EPSSG, as well as the FY orbits. So we will fly on the 330, LTDN 730 and 1130. We intend to place 2 satellites per orbit. So in total, a nominal configuration will count about 6 satellites, and they will, of course, fly at 180 degrees from each other on each of the 3 orbits. In terms of performance of the constellation, the most important figure of merit is the time to achieve 90% coverage, or at least this was one of the drivers for the constellation. And we, let's say, considering only Sterna, we should achieve about 3 hours, in 3 hours, the 90% of the global coverage. That made a grade up to 4.7 in case of satellite failure. We can actually allow some failures also in the constellation as the redundancy is in orbit. Also important is the mean time between observation, which is essentially the revisit time, which goes from 20 minutes to 3 hours, 20 minutes even below in the Arctic region, which goes back to what I was hinting before about the importance for nowcasting of this mission. I'm not sure I can activate the animation there. Maybe we can, but okay. In any case, this is just showing how the 6 satellites will achieve global coverage. Of course, this is accelerated. Otherwise, we would be watching this for 3 hours. So also few details about the satellite. So the satellite will be identical, but there are few configuration changes depending on the LTAN. In this case, so you see there are two configurations. There are in total 2 configurations. One with the 2 wings at 1130, and another one with essentially 4 panels, which is shown on the picture. So in terms of satellite and payload, so the spacecraft is a 3-axis stabilized satellite. It's a small satellite. It's about 1 meter square. It features electric propulsion and has a weight of about 135 kilos, power consumption about 140 watts, and it transmits data in L-band mainly, and it features, of course, also direct broadcast capability. The S-band channel is used only for commanding and also to repatriate data, but mostly data will be descending in L-band. There is only one instrument on board. That's a passive microwave radiometer with 19 channels, about 30 kilos, 35 watts of power consumption, very small data rate, and it's a cross-scanning instrument with an angle of about 54 degrees on each side, and achieving about 2,000 kilometers swath. You can see on the table here the different channels. So essentially, in order to achieve the mission objectives, in particular deliver temperature profile and humidity profile, we have the channels on the 50 gigahertz range. We have a surface channel, which is the 89 gigahertz one, and then at around 180 gigahertz the humidity profile channels. And novelty also here is the 325 gigahertz channel, which will allow not only humidity sounding capability, but also detection of cloud properties and ice. This is a snapshot, schematic view of the system. So of course, satellites are part of the system. On ground, we'll have a number of stations. So let's start from the left. As I mentioned in a previous slide, the commanding is done in S-band. So monitoring control is done with our legacy or our existing asset in Svalbard. So that those are the same antenna used for EPSSG. Whereas for the L-band, we will have dedicated antennas for Sterna. These are 3 set of antennas in Svalbard, which will be delivering the so-called global data. And in order to improve timeliness, we will also have 2 antennas in the southern hemisphere, in particular in Punta Arenas, also equipped with L-band capability. And the timeliness with this set of antennas for the global data, so the threshold is considered, this is the requirement, 75 minutes, but with the Punta Arenas, we will probably be below that. And if we get also McMurdo, we'll go below 1 hour. Of course, very important, especially for this forum, also the regional data service, which is achieved thanks to the direct broadcast capability of the satellite. So we will be using the EARS network for the regional service, and that will provide also quite short timeliness for the data, below 20 minutes. And then also any entity with L-band antennas will be able to acquire data. So that's what we call local data services. The data processing system, the mission control system, and all the distribution and monitoring capabilities will be at EUMETSAT, and data will be distributed through EUMETCAST to all users and stored also at EUMETSAT. So this is just showing what we are using in terms of regional stations. So Kangerlussuaq, Lanyon, Maspalomas, and Athens. In Svalbard, you may notice that Svalbard is not there. This is because we will use the dedicated antenna we have for Sterna, which will acquire both store mission data and direct broadcast data. And of course, timeliness will be, as I mentioned, below 20 minutes, between 20 and 15 minutes. In terms of deployment and replenishment strategy, as these satellites are developed along the so-called new space approach, their reliability may not be as the one of the satellites we have been flying until now. And that's why we have a strategy for replenishment, which is taking this into account. Of course, this is quite theoretical, what you see on the screen. So one anchor point is, of course, the fact that we will launch the initial constellation in 2029. The following launches will depend on how the satellites behave in orbit. And what you see on the screen is just the result of statistical analysis regarding the reliability of the satellite. So these launches will not be cast in stone, especially those after 2029. But as a matter of fact, or let's say the message here is that over the course of the mission, we are planning to launch about 20 satellites. There are two that we regard as spares, but anyway, even the spares will be launched at some point. At least this is the plan today. And you may also see from this timeline that the production of the satellites is not, it's continuous, and it's continuous until 2035. So it's not, we are not building all 20 satellites at once. So this is giving you an overview of where we are on the mission. So the approval of the mission took place early this year, but of course there was a lot of work before then to prepare the approval and also to make sure that we can deliver the system in a relatively short time after approval. And you may recognize, in fact, that several milestones have been passed even before the approval. Here I started with PDR, but there are other also milestones that were achieved beforehand. So the system requirement review, the ground segment system requirement review, the preliminary design review, and the ground segment preliminary design review were all closed. And now we are heading towards the system and ground segment CDR, which are planned in November and January timeframe. And yes, after that, we will start integrating the various elements of the system and together also with testing with the satellites and heading towards the readiness for launch in 2029. Just a few points on where we are, also on the development of the ground segment, and you may see that on that front, we are quite advanced already. So the Northern Hemisphere ground stations are almost completed. So we have conducted last year an RFI survey, so checking for interferences. We are planning now to deliver the stations, antennas, radom, and backend already in October in the Northern Hemisphere. In the Southern Hemisphere, we just started, so we conducted the RF. Thank you. We have conducted the RF interference analysis, and that needs to be continued, but we just started. The picture on the right are the one about the Svalbard antennas. You can see it's materializing. Regarding the processing facility, we have in-house already the level 1 and level 0, or at least the first version of this software. And we also have an orchestrator, and which was tested with the AWS level 0 and level 1 processor, and we are now integrating it. And the mission control system is maybe one of the few parts which are not completely reused, which is being also developed. The work is ongoing together with the mission, the multi-mission elements as well, which are undergoing a number of key points in order to deploy environment ready for this subsegment. On the space segment, we kicked off in March, and the work also is ongoing. Critical will be the delivery of the instrument, which is, as of today, at proceeding nominally. And on the launcher segment, we are also about to release the ITT for the selection of the frame contract members, because we will use a frame contract for the selection of launcher providers. Few words about Arctic weather satellite. I'll be brief. This is, of course, a precursor of Sterna. It is an ESA mission, and EUMETSAT role on this mission is just the distribution of level 1 data, level 1B data. It was launched in August 24, and data evaluation of this instrument have shown actually that the data are in line with the socioeconomic benefit studies that were then used for the approval of Sterna. We are distributing the data, as you probably are aware, and several NWP centers are planning to use those data operationally. The mission is currently funded and operations are currently funded by ESA, but this is essentially the funding are expiring or are running out as of August this year. So EUMETSAT is proposing to their member states an extension financed by EUMETSAT of this mission. And that's all on my side. Please.
All right, do we have a question? We're running over, but maybe we have time for one question for Alessio. Let me just check quickly online. I want to apologize to the people whose questions I missed this morning. It was pointed out to me that there were some questions. So I'm new to Slido and I take full blame for that, but I think I got the hang of it now. So hopefully I won't miss any.
And I will follow up on those questions. And from earlier today, the questions from Nigel's presentation, his replies have been posted to your questions. So please feel free to log into Slido and check out the answers, and we'll do the same with the other questions. But there are no new questions, Graham.
Okay. So as I mentioned, we are running a little bit behind. That's my fault. We're not keeping people to time. I think in the afternoon, we'll have to keep people a little tighter to time because we've got the EUMETSAT tour coming up later. So now we've got a coffee break, and please be back in the room. It'll be a little bit shortened. Please be back in the room by 15:50. All right, thank you.
So welcome to our final presentation session of day one. And this session will focus on direct broadcast activity in Africa. And we'll hear from EUMETSAT, and we'll also hear from several of the stakeholders from Africa on their activities to support direct broadcast on the African continent. So we'll begin with Antoine Jeanjean from EUMETSAT, who will talk to us about the status and evolution of the EA's SEWA project. Antoine.
Thank you, Liam. So here I go again. So for a second presentation there with a different focus on upgrade of station in Africa. This presentation will first look at what was done before SEWA in a project called SAWIDRA, and then we'll move on the SEWA project scope, the phases, the technical approach for upgrading the station, and what regional service are expected to be provided through this activity. So before SEWA was SAWIDRA, and SAWIDRA was another project, European Commission funded, approved in 2013, and it stands for Satellite and Weather Information for Disaster Resilience in Africa. This project was led actually from EUMETSAT side by Carlos Cabanas. He's here with us today. It was completed in Q2 22 because it has a strict deadline and the funding was expiring at this time. Since 2023, maintenance has stopped and the station have become non-functional. You have, for example, some licenses issue that stops, so no more products are being disseminated. As a result, satellite observation from the RAS station are no longer feeding the National Meteorological and Hydrological Services and regional climate centers for the issue of early warnings. This undermines the overall objective of SAWIDRA, which was to support disaster risk reduction and disaster risk management. So a bit what are RAS ground stations? So these are 4 stations built during the SAWIDRA project, and RAS stands for Africa Regional Advanced Retransmission Services. And you have here 4 stations in Gabon, Kenya, Niger, and South Africa, which cover most of the African continent, as you can see on the map. So this comes SEWA. SEWA is Space for Early Warning in Africa. It's an EU-funded program helping African institutions to use satellite data for early warnings. The scope there, I'm speaking, it has a wider scope, so I focus on the project, obviously, for the RAS, but it has also other aspects, is to upgrade the 4 RAS stations to make them functional, strengthen capacity in Africa, and share regional services with national med services and regional climate centers to support the issue of early warnings and support the implementation of disaster risk reduction and disaster risk management. So it's a kind of the continuation of SAWIDRA. There is a 3-phase delivery structure. Now the project has completed phase 1, which was to lay foundation for governance, baseline, and training framework, and is entering full implementation, which is a phase 2 between now and 28. And this is to upgrade the station, provide training, test beds, and early operational demonstration. The 3rd phase of the project will be to close and transfer, which means consolidating knowledge, feedback loop, long-term operation, and transferring assets in terms of hardware and software and knowledge to the African station operator. The technical approach to be used for the upgrade of the RAS station is, you probably very now familiar with this diagram from this morning. So there is the idea is to reuse EUMETSAT knowledge and design when possible. The BBU, baseband unit for payload data acquisition, we don't know yet which model it will be, but they will be replaced. We'll see it in the next slide as well. For data processing, there are 2 servers like in ears to be procured and shipped to the station using the same software layer as the EUMETSAT PPN. The dissemination will be local and to WIS2, and there will be in this phase 2 and phase 3 as well some remote maintenance and support by EUMETSAT. So the element to be upgraded as part of SEWA, so this is a complete end-to-end slide. There are in each station a baseband unit, so that EUMETSAT will support the procurement, and 1 processing server that will be operational and 1 validation one. So in case of need from each of the sites, if there are specific need to test and disseminate new product, it will be possible to first test them on a validation system and then deploy the operational system. EUMETSAT will provide technical support, maintenance, and facilitate training and provide training if needed. Now, we were at the beginning of the project anticipating that EUMETSAT may have to push data to WIS2, but this has progressed quite well. The station have already been interfacing with WMO to have WIS2 connectivity. So now we are anticipating a direct connectivity between each of the stations to WIS2 for DBNet contribution. There will also be regional dissemination to the national center. All right. Then for this, for the data processing, similarly to this morning, the design is to reuse EUMETSAT knowledge. So there will be payload data coming from the BBU. This server will have internet access. So you see there will be some modification in EUMETSAT. There is no internet access. In this case, auxiliary data will come from internet and dissemination will be directly to the internet as well. EUMETSAT it's a bit different, so there will be some adaptation. The approaches with orchestration and Dockerization will remain as for EUMETSAT PPN. So in this regard, there will be no changes. Changes are in interfaces, but not in the orchestration and Dockerized application per se. So for the hardware and software provision strategy, now that the project is in phase 2, EUMETSAT is conducting a procurement for the baseband unit and the PPN hardware, and this will be shipped and installed in the SEWA station. During implementation as well, the software maintenance will be under EUMETSAT, but this will be externalized to a company. For the PPN, EUMETSAT will provide the software layer, and also training will be organized for transfer of knowledge. In 28 to 29, the ownership and operation will be handed over from EUMETSAT to the SEWA beneficiaries. And from this phase 3, SEWA beneficiary will then take over hardware and software maintenance. I think I am well on time. For SEWA regional services, the plan will be to have same harmonized approach for each of the stations that will acquire the same satellite and deliver the same services. So from the METOP, it will be sounding, imager, so ATOS, AVHR, and hyperspectral with EAZ. And level 2 will be possible there as well, so it will be level 1 and level 2. For the JPSS, it will be ATMS, CRIS, and VIRS from NPP, NOAA 20, and NOAA 21 if NPP is still operational. And then for the Fengyun, it will be FY3D and FY3E, providing the sounding VAS, the imager MERCI, and microwave radiation imager, and WRI. Yeah, and then there is the cities there. So we started to look at buffer generation, and with this we need the location in terms of cities. So in Gabon it will be Libreville, in Kenya Nairobi, Niger Niamey, and in South Africa Heartbeat Shock. I don't know really how it has to be pronounced. Yes, so and this will enable as well the dissemination to WIS2 for DBNet. So and there will be a bit more detail with the upcoming presentation, which will be site specific. So I kept it at high level for this first presentation. And yeah, so thank you.
Thank you, Antoine. Are there any questions? I don't see any room. Any online? Well, maybe I'll take the chance to ask one question. So in the presentation you've just described, what are the products that would be generated by the processing computers and disseminated via GTS and WIS 2.0?
Okay, so we are not anticipating GTS dissemination. So product will be disseminated directly to WIS 2.
Just WIS 2.0, okay.
And here's a list in this slide actually of the product expected. So for you will have all the sounding services from the METOP, JPSS, and FY3. But
so just the sounding services?
No, and imager and hyperspectral. So you have.
Okay, sorry.
Yeah.
But are you talking about level 1?
Level 1, yes.
Level 1 converted to buffer?
Yes.
I assume.
So in imager, you don't have buffer. So it would be, actually, maybe I can go one by one. So the sounding will be level 1 buffer. They're all in buffer.
Mm-hmm.
EASD level 1 is in buffer. The level 2, I think, is a different format, NetCDF. So it will be level 2 as different product. And then CRIS is in buffer, MWRI as well. Yeah, so, and VIRS will be SDR. I don't think we're anticipating to use CVIRS in this case. It's not going through EUMETCAST. Mm-hmm. So it may be M-band, okay. SDR for VIRS.
So to follow up from that, is there any discussion of creating some high level 2 products from VIRS or?
Yes, I think so. The expertise of EUMETSAT here is to provide the knowledge we have with the ear station. And then after this will enable the local operator to generate, for example, flood product, fire product could be generated from the processing chain that will be there. So the idea is to provide and to enable other products that could be of use. And this is why as well, you remember in the previous slide, you will have 2 systems. So new chain can be deployed in a validation system than operational system. So the idea here is to enable capacity through the provision of level 1 product using EUMETSAT knowledge.
Okay. Any other follow-up questions? All right, thank you, Antoine.
Thank you.
So our next presentation, I believe, will be virtual through Teams, and it will be from Ali Abani Ahmed from ACMAD in Niger.
Okay.
Hello, Ali.
Hello. Can you hear me?
Yes.
Okay. Yes.
Did you want to share your slides, or would you like us?
Yes, share my slide, please, so that we optimize the button. Share my slides, then I present. Thank you. So Thank you very much. I'm Abani Ahmed Ali, working with ACMAD, the African Center of Meteorological Applications for Development. We are going to share with you the status of the RARS in Africa, which is going to complement what Antoine has just presented in reality. Next slide, please. So currently the network is composed of the 4 RAS stations of Gabon, Kenya, SANSA, and Africa and South Africa, with plus Niger, with the full infrastructure tested, installed, and tested during the Sawidra project. Next slide, please. This slide has been presented by Antoine, is actually the impact that the RAS network has given over Africa of improving the coverage of low orbit satellite data over the continent. Previously, we used to be covered a bit by the IRS network on the north and a bit of the south stations. Next slide, please. The Sawidra network actually has another component, which is the communication network. The Sawidra was planning to use the RAS station data and also share information to the Regional Climate Center, the RCCs. So the force, that component has not really been implemented when the project finished. But we are having big hope that now with the injection in the WIS system, those information will be available to all the regional centers and med services in general. Next slide, please. This is the project in figure, just to share experience that we, it was about almost 3 million euro. We went through a good experience of negotiating with the installation company, a Solotop, a South Korean company, which won the bid. So we went through the full process of establishing all these 4 stations over the period of the project. Next slide, please. So this is a bit of summary with the 4 stations installed, tested, and validated. The negotiation gave us about 3 years warranty after the end of the installation, which led us up to 2023. The equipment were guaranteed. We have also gone through some upgrade of equipment because the installation were done with the demodulator 200 and the demodulator 300 have just been installed when the warranty period ended. So we validated the site acceptance test in 2020, and also we arranged for communication for aggregation of the data through the South African hub for us to be able to put in the GTS. So we went through some discussions, basically to be able to inject the RAS station data into the DBNet, the WMO network, and also to ensure that the RAS station will improve significantly the quality of numerical weather prediction in Africa. Also, we went through some discussions about the training issues and how do you call it, the sustainability at the end. Next slide, please. This part is the very important one where we have been able to, through the DBNet group and with the support of WMO and EUMETSAT, to prepare the injection of the data through GTS. The next slide is, next slide, please. This is the key table where our station got the necessary credentials to be able to disseminate to GTS. And after the installation, all of those stations have been able to disseminate at least for some times data to the GTS based on the implementation of this table. Next slide, please. So from SAWIDRA SEWA, as Antoine just explained, the strength Africa, the new project, is now taking over. So one of the key actions was to conduct the survey to know what SAWIDRA has done and which is the current status of SAWIDRA. So regarding the indoor and outdoor units, they have been operational up to 2023, and then we confirm those status. For the indoor unit, also they have operated, tested, disseminated to the until the end of maintenance contract. Next slide, please. The software we use on the RAS station has been developed by Pink Matters in South Africa under the Solitop company. It was a full package that allows us to manage the station with all features graphically. So this is the capture of the Far Earth Observer, and we can see the satellite passes and monitoring all the station. And all the 4 stations are having the same software and the same configuration. Next slide, please. These are data harvested from the station in Niamey by then. Sample data from NOAA 20 VIRS at the time received quasi real time. Next slide, please. So currently we have the station, they have been installed and they contributed to DBNet. The first challenge was the end of the maintenance contract in 2023. And a new contract was needed. So SEWA came at the right time to take over with a new approach based on the existing one. So we have also engaged in the establishment of the new memorandum of understanding with the hosting sites, because it is a completely new situation based on the new So a new maintenance contract is now under preparation through the SEWA program. Yes, please. Next slide, please. Regarding the antenna systems, we are using the orbital system antennas. They are very robust antennas, and they are still operational. There is no challenge. The Far Earth software, the key challenge we had was that it was dependent upon the upgrade by the Pink Matter. So regularly that software need upgrade. And we have shared with EUMETSAT through several meetings, and that will be considered in the next maintenance contracts. Next slide, please. This was the inquiry regarding the reception of data. We confirmed that those stations have been receiving testing, and no challenge in terms of capacity of the system to receive. Next slide, please. During the SAWIDRA program, those were the instruments considered by SAWIDRA projects, and the table lastly presented by Antoine is giving path to the new setup and configuration for the stations. Next slide, please. Is the same. You can pass. These are the continuation of the other one. Next slide, please. So in summary, this program, as he said, was launched in 2025, the SEWA project. On our side, ACMAD, we are managing the RARS network. we have conducted 4 coordination meeting with hosting sites for this 2026 for this year. And also we are exchanging with EUMETSAT for sharing experience of the project for the better implementation. Next slide, please. Actually, ACMAD is a part of the consortium to implement the AMSAF. So the SAF now casting as part of the AMSAF implementation. So the second component considered by the SEWA project is the RAS upgrade, which is bringing us into this exchange with EUMETSAT and new contract for maintenance. Next slide, please. The current status in summary. So project was launched in 2025. Regarding the MOU, I will say that we have already drafted a new MOU. We share with the partners, and now the MOU is at the host site level. Each hosting site has the MOU to contribute and validate for next step. The current situation is that ACMAD owns the RAS stations from the Sawidra project, and hosting sites are the actual owners of the station in terms of operation and also management. So that needs to be considered to be able to facilitate for them some trainings in terms of WIS for instance, so that they best support the stations, and any other training such as the CSPP meeting and others that will allow all the host site station operators to really manage the stations. EUMETSAT is covering the upgrade of the RAS stations and this SEWA initiative. Next slide, please. This is the last slide in summary, which is bringing us to key point, which is idea of discussion on the long-term sustainability, which should be well planned at the end of this program. And SEWA project ownership, maintenance, operation cost must be well strategized, so that at the end of SEWA program, the stations will be still operational and contribute to DBNet as planned. So the approach of the project is facilitating for each host site to be part of the WIS program. They are they are making the necessary formalities, and also to contribute to the DBNet as also as DCPC, data collection and processing centers. So at the end, we are seeing the network of the 4 RAS stations Africa becoming also with DCPCs. Thank you very much. This is the last slide. Next. Thank you. This is the last slide. Thank you.
Thank you,
Any
Ali,
question?
for that background information on the Sawidra project history and the SEWA project that is in progress now. Are there any questions? Yes, go ahead.
Thank you for presenting this really exciting work. I was especially interested in what you said about the All-African Technical Support Team. Can you tell us a little bit more about the potential difficulties there, both in terms of personnel and perhaps hardware procurement?
Hello? Hello, can I? Hello?
Hello, Ali. Did you hear that question?
Yes, I hear. It's true. During the Sawidra, one of the strategy was to use the expertise of the space agencies in terms of handling space infrastructure. And another arrangement of SAWIDRA that we are still bonifying was we had EUMETSAT as a technical implementation partner. So all the technology, and Carlos Cabana was one of our focal points. We had a nice technical support to be able to provide SAWIDRA up to installation. So now we would like to keep this similar arrangement to have the team on the ground trained on the good management of the RAS stations in general. We are already in partnership during this SEWA. All the procurement is being handled by EUMETSAT, and necessary training and some technical aspects will be covered by EUMETSAT. Thank you.
All right, thank you, Ali. Any other questions?
I have a question maybe for Antoine regarding all the infrastructure of like in each hosting site, if they bring the new PPN and BBU installed, what will be the fate of the previous indoor units? Are they not going to be used? Are they still usable and so on? Like the current
Hi, Ali. I think for now, for now, it's important to keep it because you have some element of the chain, like the deplexer, that should stay there. But then when the new system comes, there will be some element like the EOS, FES, and the Far Earth server. Those ones, they will not be needed anymore, and you will have a diagram with all the necessary steps for installation of the new hardware with a step-by-step procedure. So for now, you have to keep everything, and then when the shipment comes, there will be an instruction manual on what to dispose and how to install the new hardware.
Okay, thanks.
But as a summary, for now, keep everything, but the EOS, FES, and Far Earth will not be required. But yeah.
Okay, great. Thanks.
Okay. Let's move on to the next presentation, which will be from Allan Oware from IGAD, Climate Prediction and Application Center in Kenya. And it will be on RAS Africa, building operational EO data pipelines using CSPP and Apache Airflow.
Good evening. I'm Allan Oware. I'm a remote sensing specialist from the IGAD Climate Prediction Application Center. My presentation will be building upon the two previous presentations regarding the RAS Africa network. So I'll be concentrating in the context of the East African hub. Just to give a brief overview of ICPAC. So ICPAC started as a drought monitoring center back in 1989, and in 2012 it was designated as the IGAD Climate Prediction and Application Center. So this is a specialized institution of the Intergovernmental Authority on Development. That's IGAD. So IGAD is a regional economic commission covering the Eastern Africa region. So in 2017, ICPAC was designated as a regional climate center under the World Meteorological Organization. So ICPAC strives to be a center of excellence in terms of climate services for sustainable development in the Greater Horn of Africa. In terms of geographic coverage, so ICPAC covers 12 countries. So these comprise of the 8 IGAD member states in the Horn of Africa and plus 3 additional countries. So in total, there are 12 and basically populated by around 400 million people. In terms of the key services for IGPAC, so we are majorly focused on climate monitoring and forecasting, but we're also looking at climate change adaptation, agriculture and food security, water resources, environmental monitoring, disaster risk management, in which satellite data and applications are critical. So in terms of, for the recent 2 decades, there's been an interplay of climate risks in the Horn of Africa, starting with the severe droughts and widespread famine, the El Nino phenomenon, tropical cyclones. We even had a very severe desert locust infestation. This was in 2020, and we're also experiencing severe flooding and destruction of property. So these climate risks require continuous monitoring and forecasting in terms of robust early warning systems. So in terms of the data infrastructure, due to the unique relationship of IGPAC has access to ground station data from weather stations from the national hydrological hydromet stations services. So basically, using the ground data, this is blended with the satellite-derived data to provide the forecasting products. In addition, through collaborations with institutions such as EUMETSAT, we have been supporting the national institutions to access satellite data for weather forecasting. So we basically support the institutions in operating satellite receiving stations across the region. So in terms of the RAS station, so this was installed through the SAWIDRA program as the representative from ACMAD stated. So it was installed in 2019, to provide access to polar orbiting satellite data from the NOAA satellites, the METEOP satellites, and also the FY3D satellites. And in terms of the applications, so the applications included the climate monitoring, natural disasters, vegetation monitoring, agriculture, air pollution, and also temperature. So in terms of the data processing framework, so we are basically leveraging on CSPP and Apache Airflow for the data pipeline. We're also using Pytrol for the image generation. So in terms of the products, so the first 2 presentations for the RAS focused on the level 1A and level 1B, but we are also interested in the level 2 products. For example, the fire detection products, active fire, burnt area mapping, the flood detection, surface reflectance, the vegetation indices, land surface temperature, and also the atmosphere environmental data records. So in terms of the features that we are leveraging on Apache Airflow, this includes the DAG orchestration, the scheduling, the task passing of data, and also the logging and metadata. For the, I will basically also get into the operational use of the DB satellite products. So basically, what is the demand for these satellite data products? So at IGPAC, we are hosting the IGAD, the IGAD Disaster Operations Center. So this is an integrated regional multi-hazard early warning system. So the main hazards we are monitoring in Eastern Africa include floods, drought, food insecurity, pests, tropical cyclones, landslides, forest fires, and also epidemics. So this is one of the 4 situation rooms in Africa, together with the African Union, the ECOWAS situation room, and also the situation room in ACMAD. So the main services include hazard monitoring to coordinate early action, rapid mapping of the affected areas, and also capacity building on anticipatory action. So IGPAC, through the Disaster Operations Center, operates the East Africa Hazards Watch. So this is a one-stop shop in terms of information for both the monitoring aspect and the forecasting aspect, and especially integrating the satellite-derived data sets with the socioeconomic data so that you can basically forecast impacts whenever disasters are going to happen. So we're looking at extreme rainfall, temperature, agriculture, also pests, flooding, and also tropical cyclones. So I will go through some of the applications within the East Africa Hazard Watch system. So we have the East Africa Drought Watch. So this is a dedicated application, early warning system, which is basically utilizing satellite-derived data sets in terms of the vegetation indicators, soil moisture indicators, precipitation, to basically come up with a combined drought index. So this will be able to indicate at subnational level which areas are under drought alert, warning, or watch, so that to advise the necessary national governments to act in terms of to alleviate the impacts caused by drought. We also have the East Africa Agriculture Watch. So this is also using satellite-derived indicators for monitoring agricultural productivity across the croplands and rangelands of Eastern Africa. So this platform was developed in conjunction with the European centers, for example, the Joint Research Center. And also within the East Africa Hazard Watch system, we also have the East Africa Flood Watch. So the Flood Watch incorporates hydrological modeling outputs together with satellite-based flood monitoring to basically to provide monitoring information of floods, and also to forecast, since we are using calibrated ground data. So we're also able to forecast floods across riverine floods across different basins in East Africa. So going forward in the context of the SEWA, the SEWA program. So the SEWA, basically through the EUMETSAT implemented program, the RAS infrastructure will be upgraded, will undergo upgrade in terms of the acquisition and processing. So basically we'll be working together with EUMETSAT and other contracted institutions to upgrade the RAS infrastructure. We'll also be looking towards automation of the system in terms of the acquisition and processing. So right now the gaps have already been identified through the presentations by Ahmed and by Antoine. So we'll also be incorporating the WIS2 transmission of the level 1A, level 1B products through the WMO platform. So all these data sets also have to be integrated through the AMSAF. So that is the Africa Meteorological Satellite Application Facility. So we'll be working together with the national MET institutions to be able to ingest the data products, and to be able to also to incorporate these products into the NWP models. So the data that is coming through the RAS is also important for predictive analytics. So in terms of pushing this data to integrate with the predictive models. So basically, for example, we have the predictive livestock early warning systems, and also the impact-based forecasting. Besides this, we also have some demand for new regional data services. For example, the Marine Watch. So the Marine Watch will be integrating data from the RAS to provide ocean color products. We have the Pest Watch, the East Africa Pest Watch, which will also be looking towards monitoring the environmental conditions which provide information on pest infestation across Eastern Africa. And also we also have demand for air quality and pollution monitoring. So thank you very much for your attention.
Thank you, Allan, for your very interesting briefing. Are there any questions or Allan? Yes, we have one from Antoine. He had his hand up first. Or maybe Carlos. Go ahead.
Thank you. Thank you very much for the presentation and for all the support for the SEWA project. So the question is, within the framework of SAWIDRA, we establish operational services delivering level 1B products from the American, Chinese, and European MET polar satellites. Did you establish level 2 applications on products from the SAWIDRA services, like these ones that you mentioned, the Marine Watch, the Pest Watch, air quality? Have you implemented any of these services with the data of SAWIDRA?
Okay. So in terms of the level 2, in terms of the level 2 services, basically this came after the SAWIDRA project ended. So basically we were able to basically try to we basically reestablish the data processing pipeline, since I think after SAWIDRA the processing, there were some issues with the processing, but I think because of the demand that is there, we were able to reconfigure, re-engineer the data processing pipeline. That's why we were mostly focusing on the level 2 products. Yeah.
Okay, I have another question, if I may, very fast. Yes. So when we installed the antenna, we were very concerned about the weather conditions and the wind. Because there were high winds there, and we were concerned about the health of the antenna and if it could cope with the winds. So at that moment, we were analyzing whether we had to install a radome or leave the antenna as is. Yes. Did you have any problem during this period with the antenna?
We didn't have. I didn't note any operational issues with the antenna hardware. Yeah, so far. Yeah.
Thank you.
Antoine?
Thank you, Liam. So yeah, actually it was related to the question of Carlos. So it's more a comment for me is that with the new project, the software layer will provide, you had a slide with the VIRs level 1 and level 2. So RDR and SDR, they will be provided with the software platform as it is. So you will have VIRs SDR that you can use, so you can focus already more on the level 2 pipeline. And because SDR will be provided with the EUMETSAT software layer. So it's more a comment, regarding your slide.
Yeah. So yeah, my presentation also touched on some of the local applications which we'll be concentrating on. So apart from the level 1, the level 1A, level 1B products which will be integrated in the WIS2, we'll also be focusing on the level 2 products, especially the context of disaster risk management.
Because this is not provided, so yeah, this is something that you have to keep. If you have to focus attention, it's good to focus because SDR will come as is. So all the rest is something you have to work on. Yeah,
true. Thank you.
Any other questions? Yes.
Excellent talk. You did mention tropical cyclones, hurricanes as an area of environmental threat, or is it covered under marine? You get a lot of cyclones in Mozambique and Madagascar region in the areas of applications.
Yes. So we do get a lot of tropical cyclones, especially on the Western Indian Ocean region and also towards the Horn of Africa, the Somalia region. So we basically, apart from the polar orbiting data, we also have access to the geostationary satellite data through the Meteosat, the MSG and also MTG, so which provides a higher temporal resolution. So this is something which we are working with the national or the national Met agencies, in providing access to the data.
Thank you.
Thank you.
Any other questions? Okay, I have one. So, Allan, I thought it was very interesting when you showed your DB workflow and you described using Apache Airflow. Interestingly, at Wisconsin, we have a little bit of experience with that as well. Yeah. What made you choose Apache Airflow? What do you think its advantages are over other techniques for doing the same job.
So yeah. So previously we had a very manual workflow in terms of the data processing. So I think Airflow came in terms of the automatic so it's the automatic ingestion and also the activation of the data processing. So that's why we opted for Apache Airflow. So but in terms of, so we haven't used it for a very long time, but it's something which is it's basically it's serving our needs for the time being. But we'll have more. The whole processing pipeline will be upgraded to a more robust system. Yeah.
Okay, great, thank you. If there were no more questions, then we will move on. And for the last presentation, we will hear from Themba Mbule, I hope that's close, from SANSA in South Africa on SEWA activities at SANSA. Here we go.
Good day, everyone. I am Themba from the South African National Space Agency. Just a brief introduction to the South African National Space Agency. It was established in 2010 by the South African government, and we do report to would give reports to the South African Parliament. And the mandate includes promoting and using space to foster cooperation in space-related activities, encourage research in space science, advancing scientific engineering through human capital, and then creating an environment conducive to industrial development in space technologies. I would like to play just a short video to introduce you to the South African National Space Agency.
Humans have always been fascinated with space, trying to understand our universe and pushing the boundaries of our scientific and technical limits. The current era of space exploration is focused on developing our capability of sending humans deeper into space than ever before, beyond the low Earth orbit and eventually even to Mars. But even more than these journeys of discovery, we have all become heavily reliant on technology to support our way of life. Knowledge of and from space improves our ability to manage and sustain our natural environment and resources, increase the mobility of people and products, and deal with health and security threats. It offers instant communications, enables us to accurately observe and locate any spot on Earth, and empowers us to timelessly foresee and deal with economic and human catastrophes. Since the advent of the space age in 1957, South Africa has established a reputation for accuracy and reliability in the international space community. The SANSA Space Operations Directorate has provided state-of-the-art and globally competitive satellite tracking and ground support services for more than 60 years. Its presence provides a world-class ground station on the African continent, and the program also conducts applied research, development and innovation in space operations, and focuses on developing human capital in this sector. This SANSA facility is perfectly positioned geographically, on a farm in Hartebeesthoek in a remote area of the Magaliesberg mountain range. The antenna farm is 135 hectares in size, and its location is in a region with little wind and no significant seismic activity. At 1,553 meters above sea level, the site provides an excellent horizon mask for tracking low-orbit satellites and supporting low-elevation acquisitions. The site is classified as a national key point site and is under constant security surveillance. The SANSA Space Operations Program is acclaimed for its infrastructure, cutting-edge communications, and the experienced operations team. Space operations is ideally positioned as a center for tracking, telemetry, and command for geosynchronous, polar orbiting, and scientific spacecrafts. The facility has over 60 years of experience that started with NASA and the Jet Propulsion Laboratory. Subsequently, it has provided services and support to space agencies and aerospace companies around the globe. SANSA has established itself as the most reputable tracking station on the African continent and currently operates an array of over 50 antennas with different dish sizes and slew rates and accommodating a number of frequency bands and tracking modes. The ground station provides launch and early orbit support services for international space missions from different launch complexes into different orbits, downloading rocket telemetry, and providing TT&C during the early phases of a new satellite deployment. The facility functions as a telecommunication hub for connecting a satellite network with terrestrial networks to provide high-quality satellite communication services to record information or operate guidance apparatus. Today, SANSA continues to apply the benefits of space science and technology to help grow and develop the African region. We look forward to continuing to provide clients with the accuracy, reliability, and service excellence that has become the norm from the truly remarkable team at Hartebeesthoek.
Thank you. Just to go ahead and summarize it, under SANSA, we have 4 directorates: Earth observation, space operations, space science, and space engineering. So for SEWA, 2 directorates are involved, which is the Earth observation, which deal with the end product, and then space operations, that's where the hardware will be installed or is installed. All the 2 directorates are in the Gauteng region. It is extending to the Western Cape currently for deep space operations. So these are some of the infrastructures that we have. They are all operational and still developing as well. So space operations, the history is very long, since 1958 up to 2023. Well, as it evolves, the names changes up until now. We have SANSA. So as far as the satellites, we offer low launch. We support launch vehicle support, low and orbit phase IoTs, routine operations. We host hardware as well, and even the end of the satellite itself, we do support that phase. So these are the current partners we have. So it would seem we'll be adding, or EUMETSAT is there already. So we are growing, and these are the support partners as well. So we cover pretty much all the essential bands. All the information has been covered here with all the antennas. We are up to 93 now at this stage. So this is the SEWA antenna. I am the technician which is assigned to. So The hardware as it stands is operational. Everything works and is still being used currently. So under the RAS satellite disaster early warning, this now is information coming from the Earth observation. This is the intended and the current use of the SEWA data, or SAWIDRA data. So these are the satellites that are going to be monitored and sensing equipment. So the target will be on the severe weather as far as METOP B and C is concerned. And then NOAA 19 also for SEWA for severe weather modules, and the NPP together with NOAA 20 and 18 and FY3D. So operational applications within the DST will also include flood and early warnings, which involves RAS sending, strengthening NWPs and quantitative precipitation forecasts. And then severe weather now casting. Then there was wildlife weather support together with drought and water vapor monitoring. So this is the ingestion process of the data. The way it is intended to be received, then processed, ingested, and then the hazard layers, risk indices, surface by LeafJet dashboards. Yeah, this is now beyond my scope of work. So, but this is how they intend to use the data. And this is the latest case. I think we had floods in KZN, which is another province in South Africa, where there is one of the biggest harbors as well. We did get rainfall warning around, I'm not sure of the date, but the rainfall expected was 100 millimeters, and it did come, and there were floods. We did lose 1 or 2 lives, which is one too many, but we did save lives. So as far as EUMETSAT and SEWA, we are forecasting at storm speed across Africa. And thank you very much. Yes.
Are there any questions? Maybe I could ask one. I think almost the last slide you showed, which was the eco-AI environmental intelligence. The last slide you showed, which was the looked like a dashboard for the eco-AI environmental intelligence. Is that system currently ingesting satellite data like flood detection or fire detection?
Yeah, it is tracking now as it is.
It is.
Yeah.
Is that data coming from the antenna system or from an archive at EUMETSAT? Where's that data coming from?
There is still currently one tracking, but I'm sure mostly it was used from the archives.
Okay.
Yeah.
All right.
But it is still operational and being used as it is.
Okay, thank you. Any other questions? Okay. Well, we'd just like to thank the presenters in the session this afternoon. So the next item on our agenda is the EUMETSAT operations tour, which is supposed to start at 15 minutes past the hour. I'm guessing it's important that we start exactly at that time. Right, exactly. So we should take a little...
So we can have coffee outside and see what's left there if you want.
Yes, we can. We can take a short break, but then maybe at 17:10 or so.
I'll go and have a look now. I'll come back down.
So Nick will go check out the situation, and he'll come back at 17:10 to lead us to where we need to go. Great. Thanks, Nick. So let's take a little break until about 10 after the hour. And don't forget the icebreaker reception is starting at 1800 and will be in the same place as we had lunch today in the cafeteria. Okay. All right. Thank you.